the nodes visible, like the one node
Yes,
file.
yes,
Yes.
yes, ma'am. Yes.
Okay. So we'll start with the week 8 problem solving session. So in the lecture, we see in the lectures what was discussed was chromatic number, chromatic index, and planar graph. So the format of the session is as before. First we'll recall all the relevant concepts, and then we'll solve some problems related to it. So first thing that we will be discussing is the chromatic number. So before defining chromatic number, we'll define what is K colorability. So when do we say that a graph G is K colorable? So we will say that G is K colorable if we can color the vertices of graph with K colors, and the rule is that no two adjacent vertices should have same color. So if there is an edge between two vertices, like if there's an edge between v1 and v2, then v1 and v2 should be given different colors. So no two adjacent vertices can have same color. And if this rule, if we follow this rule and we can color the graph with K colors, then such graphs will be called K colorable. Then the chromatic number is basically least number of colors required to color a graph G. So so minimum number of colors that are should be used for a present graph G will be the chromatic number of G. Now let's understand this chromatic number with some examples. So let's look at the very simplest example. So null graph, basically a null graph is we have only the vertices and there are no edges. So the chromatic number of such graph will be 1. So can anybody tell me why the chromatic number for null graph is 1?
Because, ma'am, they are not connected, so we can give only one color to all the nodes.
Yes, right. So we can give color, one single color to all the vertices, because there is no relation in, there are no edges. So if we give this same color to all the vertices, then the rule is satisfied that no two adjacent vertices have same color. Therefore we see that chromatic number of null graph is 1. Now the second example is bipartite graphs. So we see now bipartite graph is, by definition, we can divide the vertices of graph in two partitions, A and B, and we have that within A there are no edges and within B there are no edges. So we see if we give one color to the vertices in A and the second color to vertices in B, then this rule will be followed, and the bipartite graph can be colored with two colors. So we see that chromatic number of bipartite graph is 2, because we at least need two colors. So this we have shown that this is two colorable, but since this graph has edges, we need more than one color. Therefore we get that chromatic number is for a bipartite graph is 2. Now what about trees? What do you think? What should be the chromatic number for trees?
Two, ma'am, two.
Reason why it should be 2?
I'm saying, suppose if we start with first root as a red,
Yes.
then we can give next as a blue.
Okay. Yeah. Or
Then again,
yes, you're right. Like we can do that, or from beep also we can see that. So aren't trees bipartite graph, right? Since tree has so trees are also trees are specific examples of bipartite graph, right? Particular examples. And for bipartite graph, we have shown that the chromatic number is 2. So from B part directly also we can conclude that chromatic number of trees is 2. So is it clear to everyone?
Yes, ma'am.
Okay. Now the next example is complete graph. So what do you think should be the chromatic number for complete graphs? Kn. So first of all, K3. What is the chromatic number for K3?
it is three, ma'am, three.
3.
Okay, why it is 3?
Because if we give one red, one blue, then third one should be green because if they are
Every
all
vertex
connected.
is adjacent with all other vertex.
Yes, every vertex is adjacent to all other vertices. So basically, if we pick any two vertices, there's an edge between them. So no two vertices can share the same color. So we cannot have that two vertices with same colors, and since there are n vertices, all the vertices should have distinct color. Therefore, chromatic number for complete graphs should be n. Now next is even cycle. So we are taking C2n. So even cycle. What should be the chromatic number for even cycles?
2.
2. And reason, please? So what should be the reason why it is 2? Yes. How can we color it by two colors?
Because it has even length,
Hmm.
so adjacently we can color with 2 colors.
Yes. You mean alternatively. So basically,
Alternative.
yeah. So if it is an even cycle, we can alternatively we can pick two colors. So we can color all the odd vertices as red, say, and all the even vertices as blue. And now V1 is red and V2 is blue. So we see that we can color C2n with two colors. And since this graph has an edge, we cannot color it with one color. So the least number of colors required to color C2n is 2. So we see that chromatic number of C2n, that is even cycle, is 2. What about odd cycles? What is the chromatic number for?
Three, ma'am. Three.
Okay, why it is not 2?
Ma'am, again, because first and last we have to connect.
Yes.
So that is why.
Yes. So basically, if we apply the same trick, now if we do like if we pick all the, or like initially we start with coloring red, we give first red color to V1, blue color to V2. Now since they are odd vertices, if we keep on doing this alternatively, we'll see that the last vertex will be of red color. But this cannot happen because V1 and V2 and minus 1 also are an edge. So we'll have to give a different color to this vertex, and that is we need at least, so this cannot be colored with this cannot be colored with two colors. So we need at least three colors, and we can color it with three colors. Therefore we see that chromatic number of odd cycles will be 3. Okay, so these were simple graphs. Now using these simple graphs also, now if we have a more complicated graph, then how do we find the chromatic number? So we have discussed some results in the class that we have some bounds on this. So if we have some bounds, we can use those bounds to compute the chromatic number for more complicated graphs. So first bound is that chromatic number will always be greater than equal to n by alpha g, where alpha g is the size of the largest independent set. Second is that if G is a subgraph of G prime, G is a subgraph of G dash, then chromatic number of G will be less than equal to chromatic number of G prime. And this is very obvious because if for G we need at least 5 colors and G is sitting inside G prime, so that portion of G prime will require 5 colors. So we see this, and this theorem is this result is important in the sense that, so if you see any common graphs above which is sitting inside your graph, so suppose your new graph, complicated graph, has an odd cycle. So from this you can directly say that if it has an odd cycle, then we need at least 3 colors. Similarly, if it has some complete subgraph of order n, G has some, then from this we can conclude at least that graph should have n colors. So this kind of result gives you an upper bound. This kind of things gives you an upper bound on the chromatic number of the graph. And so this was what I was saying is the third result. So if WG is basically the size of largest clique means clique means the complete subgraph of G. So if Kn is contained in G, then we know that we need at least n colors. So we look at the largest complete subgraph, and the original graph will require at least those colors. Then another important bound is that using the greedy algorithm, we can conclude that chromatic number will always be less than equal to maximum degree plus 1. Delta G plus 1, where delta G is the maximum degree. So So given a graph G, and if you have to find the chromatic number, first step is to find the maximum degree so that you know what is the upper bound. So if suppose maximum degree is K, then you know you need, at most you need K plus 1 colors, and then you keep on seeing how many less colors you need. And this is important in this sense that this bound del G plus 1, that this bound is attained only by Kn or C2n plus 1. So that is that chromatic number is equal to maximum degree plus 1 only for these graphs. That is if it is a complete graph or an odd cycle. So using 4 and 5, lastly we can conclude that if we have a graph G which is neither a complete graph nor an odd cycle, then the chromatic number has to be less than equal to the maximum degree. Has to be less than equal to the maximum degree. So this was what was about chromatic number. Now analogous to chromatic number, in chromatic number we were coloring the vertices of the graph. Now the second thing is, instead of coloring the
Ma'am, last one is not clear, ma'am. Last one, sixth one.
yes, okay. So last one I am saying, so fourth and fifth is clear to you?
Yes, ma'am. Yes.
So now see, fifth one is saying that chromatic number is equal to maximum degree plus 1 if and only if G is K complete graph or an odd cycle. So this result is itself saying that if that G is not equal, if G is not none of these among these graph, if G is not either a complete graph or an odd cycle, then the chromatic number has to be less than equal to the maximum degree. Okay, is it clear now?
Hello.
Hello,
Hello,
hello.
Nidhi madam. Hello.
Yes, yes,
Hello.
yes. Hello. Am I? Hello. Am I audible? Hello.
Yes, ma'am. Yes, yes, yes.
Sorry, like there was a power cut, so so hence the I got, but I'll present the screen again. Hello. So yes. So now, so I was saying, so we were clearing the sixth point. So the sixth point is that if G is not a complete graph or an odd cycle, then we can directly say that the chromatic number will be less than equal to the maximum degree. So is my screen visible?
Yes, yes.
Yes, right? Okay. So the last point that we were discussing was this. So now is it clear? So there was a doubt in the sixth
Yes,
point.
yes, ma'am. Yes.
Okay. So now once we have done the chromatic number, the next thing is chromatic index. So in chromatic number, we were coloring the vertices. Now the next way to color a graph is the edge colorability. So we'll say a graph G is K edge colorable if all the edge, now instead of vertices we are coloring the edges, and what is the rule that if two edges are sharing a common vertex, then they should be of different color. So we'll say that G is K edge colorable if we can color the edges with K, if we can color the edges using K colors, and no two edges which have common vertex have same color, and the least number of color required to color edges using this rule will be the chromatic index. Now unlike chromatic number, chromatic index, we'll see that we have both a lower bound and upper bound. So chromatic index will always be greater than equal to the maximum degree. That is obvious because if suppose V1 has degree n, suppose V1 has the highest degree, say del G equal to n. Now all these edges are sharing this vertex V1. So all these edges should have different colors. Therefore, we see that the chromatic index will always be greater than equal to the maximum degree. And then there's this another result that it has to be less than equal to maximum degree plus 1. So combining 1 and 2, we can see that there are only two possibilities for chromatic index. That is, either it can be of it is equal to the maximum degree or maximum degree plus 1. And the graphs which have maximum degree chromatic index equal to the maximum degree, those kind of graphs are the class 1 graphs, and the graphs which have chromatic index equal to the maximum degree plus 1, they are the class 2 graphs. Now the common examples where maximum degree is where chromatic index is equal to maximum degree plus 1 are regular graphs of odd order. And in particular, you can see complete graph on odd number of vertices or odd cycles. For odd cycle, the chromatic index will come out to be del G plus 1, maximum degree plus 1. And in this classes, bipartite graph, even cycles, tree. So we'll look at some questions to compute the chromatic index also, so that this becomes clear. So let's look at the questions now. So now first is this question. So we are given this graph on 5 vertices. We have to find the chromatic number and the chromatic index, chi g. So first of all, if we have this, so the first step is to find the maximum degree. So what is the maximum degree of this graph?
4.
The maximum degree of this graph is 4. So now so we get that both, so the chromatic number should be less than equal to 4. That is, we need less than 4 colors. So what do you think should be the chromatic number for this? Basically, how many colors do we need to color the vertices of this graph? So look at this graph, think about it and then answer. So what do you think? How many colors do we
Ma'am,
need?
four colors, ma'am.
Okay. So
Because it is complete graph. No.
this is not a complete graph.
Yes.
So if it was a complete graph, K5, then we need 5 colors. So
Yes, ma'am. Yes, ma'am.
So now it is not a complete graph. There is one edge missing. So now how many colors do we need?
4, ma'am.
4. So 4, if you are saying 4, so first, like, what should be the, like,
Ma'am, 3 colors, ma'am. 3 colors.
oh, somebody said 3. So, okay, so how can you color this graph with 3? So can you tell the
Ma'am, labeling the vertex from A 1, 2, 3, 1, 2, 1, 2, 1.
So yes, he is right. So he is right in the
Yes,
sense. So see, this graph has an odd cycle. So we know it should be greater than equal to 3. So since this graph has an odd cycle, we know chromatic number should be greater than equal to 3, and we also have that it should be less than equal to 4. So from these two things we see that chromatic number will either come out to be 3 or 4. But now the question is, can we use 3 colors to color this graph? So somebody said yes. So suppose, you have to tell me the coloring. So what, like, suppose the colors are red, blue and orange. So what all vertices should be of red color, what all vertices should be of blue color, and what should be of orange color. So if you are saying that it can be colored with the vertices can be colored with 3 vertices, you have to give a coloring of 3 colors. So what 3 colors should, like, if it is, so first of all, is it 3 color, what is the chromatic number, 3 or 4? Any guesses?
A, C, red.
Okay.
Um,
AC
B,
red.
E, blue.
AC red. Okay. BE.
B, E, blue.
BE blue. Okay.
And D with O.
D with O. So is it
Not possible, not possible. Not possible. Because A
because
and
A and
uh,
C cannot have same colors because there is an edge between them. So this is not three color. So if you are not able to find a three coloring, let's see. So suppose so let's see. So suppose I am giving, let's see if we can color it with three colors. Suppose I am giving red color, I am starting with A. Now I am giving A as red color. Now now A is adjacent to C, D. B, so now A, A and B should have different colors because there's an edge between them. So let's say we'll give a blue color to B. Now AE should also have different colors. But since AE should have different colors, but since BE is not an edge, we can give blue color to B, right? There is no, we can give blue color to B. Now for C, we can now for C we cannot give either red or blue because we have this. So we'll have to give a third color to C. What about D? Can we give any of the three colors to D? Red, blue or orange?
not, not possible.
Not
No,
for
no, no.
not
That is why it
possible.
So
is
it is
four.
four
That
colorable.
yes, since it is not possible, therefore we see that we cannot color this graph using three colors. We need at least four colors. Therefore we see that chromatic in number is 4. So is it clear? Why is it 4?
Madam, please explain, madam, again explain.
Yes. So I am saying like, so I am starting with the any of the vertex and starting giving the colors. So suppose I started with this vertex A. So it will work with any of the we can start with any vertex, it will work. So I'm starting with A. Suppose I'm giving green color to A. Now if I'm giving green color to A, since A, B are adjacent and B, E are adjacent, B should have a different color then green. So we'll give second color to B. Now let's look at C. Now since C is adjacent to B also and C is adjacent to A also. So we cannot give green color or green or pink color to C. So we'll have to give a third color to C. There is no other option. So we give third color to C. Now if we look at D, D is also adjacent to ABC. So we cannot give any of these three colors to D. So we'll have to use the fourth color. So I'm giving this dark blue to this. Now what about E? So I cannot give these two, the color of D and C to it, neither the green color. But I can give pink color to E because there is no edge between B and E. So I'll give the pink color to B and E. So we see that it can be colored with at most 4 colors. Because for
Clear,
coloring
ma'am,
D,
clear.
we needed of this. So we have that it is 4 coloring. Okay. Now what about the coloring edges? If we are coloring edges, how many colors do we need? So first of all, what are the two possibilities for the chromatic index? So what are the two possibilities? If we are coloring edges, what are the two possibilities?
Maximum degree plus 1.
Yes. So in this case, what are the two possibilities for this graph? Maximum degree is 4. So it can be either 4 or 5. So it can be either 4 or 5. So now let's see what is the number. So so we can so we have that. So first we have to see if we can color the edges using 4 colors. So do you think we can color the edges using 4 colors? Try and see if 4 colors are sufficient, or do we need a fifth color? So if anybody is able to color it with 4, then we are done. But if nobody is able to color with 4, then we'll have to give an argument why can't we use 4 colors. Okay, so let's try.
Four,
Yeah.
four color.
Oh, you are able to color it with 4 colors?
Uh, I'll check once.
Yes. Okay. Or maybe you can tell, like we'll see. So what is the color that you give to red, your AB edge?
Yeah.
Yes. So
A,
yeah.
AB. AB I given green.
Okay. AB is green.
Uh, AE is red.
AE is red. Okay.
Then ED is blue.
EB is no, there's no
ED,
edge.
ED.
ED is blue. Okay.
Blue.
Hmm.
And BC also blue.
BC also blue. Okay.
Blue. CD red.
CD red. Okay. Till now you are okay. So
Mm.
till now there is no violation, right? Yes. Now
And A to C I have given yellow.
yellow. Okay. A to C. Yeah, fine.
Then C to E again green.
See, we cannot give green color. Acha, we can give C2E green color. Okay. Yes. Hmm.
And from D to A is missing.
From D to A is
We cannot give blue, red, green.
yellow. So if we look, yes. So if we look at the edge DA, we
We cannot
cannot give
give
it red
red,
color. We cannot give it yellow color.
blue,
We cannot give it a green color.
blue, green, everything.
So yeah. So so in this manner we cannot give it 4 colors, right? This. So you are not getting 4 colors, right?
Yes, yes.
Okay. So anyone else?
Five colors, ma'am. Five colors.
Okay. Yes, 5. Yes. The answer is 5. But so we have to give 5 colors. Okay. But why do you think we cannot use 4 colors?
We'll use that property that inside the subgraph, if we are not able to give, will take any subgraph in which 4 colors is required. So
Hmm.
then we will say this is the what you say subgraph of that main graph.
Hmm.
So that is why fifth color is also required.
Huh. So which graph you are saying? Like for which graph 5 colors are required?
If you take Any two triangles, ma'am. Any two triangles like upper triangle and lower triangle if you take.
Okay.
So then there is a four, that is a subgraph, and which will take four colors.
So this graph you're saying, right? This triangle, these two triangles
Odd
what?
length.
I have taken different, but you can take this also.
Ha.
Yes.
Okay. So you have
Ma'am,
taken, yes.
it's cycle of odd length.
So if it is a cycle of odd length, then we can only say that we need at least three colors. We cannot say that like we need five colors, right? So if we have a cycle, then we need three colors, at least three colors. Okay. So you were what triangles were you taking?
ACD and BCD.
A, C, D, and B, C, D. Okay. So if you are taking A, C, D, and B, C, D, yes.
Yes,
Okay.
ma'am. Four colors are required.
Huh. So but that is just saying we require four colors. But then so we
That is a subgraph of that main
huh?
graph, na ma'am.
Yes, but that doesn't say that this original graph will also require four colors. This will so if a subgraph requires four color, then the other graph will require four or more colors. We cannot guarantee that the bigger graph can also be covered with four colors. Because see, every graph, if you just take single edge, it is an subgraph of every graph, and an edge requires only two colors. But not all graphs can be covered with two colors, right? So it just you the
Yes, yes.
so the property is that if G is a subgraph of H, and if G requires k color, then we know that H requires at least k colors, but it can be more than k also. Okay, so I'll tell you why we need five. So why we need five colors. So let's see why we need at least five colors. So suppose I pick my color, suppose I'm taking red color, or my color one is red. So what so can anybody tell me what is the maximum number of edges that I can color using red color? So if I fix my color to be red, so what is the maximum number of edges that I can color using red? Or question is, can three edges in this graph have same color?
Three.
Oh, okay. So can you color three edges with same color? So somebody said three. So what three edges can you take? So the question is,
For the original graph, ma'am, because
yes,
the
this one.
graph which you have drawn is not
Yes, this original graph, G1.
original. We
For
can
original.
color AE.
Okay, so we can like AE, yeah, AE, then
No, it's
then
not possible.
So basically, yeah, this is the question. Can we do can we do can we use one color to color three edges? No, right? So suppose I am coloring this as red. Suppose I am coloring this as red. Then any other edge that I am coloring red should not have vertex A or E. Suppose then so basically I have to take some parallel edge. So I can take BD. Now if I have used two edges on one color. Now can I also have a third color with edge red? No. Can I have a third color with an
No,
red edge?
no.
Third edge with a red color? No, because any other edge will have either vertex A, B, D, or E. Since this graph has five vertices, since this graph has 5 vertices and 2 edges has covered all these 4 vertices. So now if we take any other edge, if we take any other edge, then it will have at least one common vertex. So is it clear that if we have one color, there can be at most two, at most, so the claim is that there can be at most 2 edges of same color. We cannot have more than 2 edges of same color. Is it true? Is the argument clear? Why we cannot have 2 edges of same color, more than 2 edges of same color?
Yes, yes.
So now, how many edges does this graph have? So this graph has 9 edges. So if we can, this graph has 9, so we see that this graph has 9 edges. So now, if we have to use only 4 colors, we can color at most 8 edges. Therefore, but this graph has 9 edges, therefore we need at least 5 colors to color the edges of this graph. Is this clear? Why we need 5 colors?
Yes, ma'am.
Clear to everyone? So I am just saying that there we need, so the claim was this, that we can color only at most 2 edges with same color, but this graph has 9 edges, so we cannot color using 4. We need 5 colors. So we see that chromatic index of this graph is 5. So is it clear? Clear to everyone? Okay. Any confusion in this question? Okay. So next, move on to the next one. So for this graph, what is the chromatic number? So how many colors do we need to color the vertices of this graph? So first step is to find the maximum degree. So what is the maximum degree?
Three.
Maximum degree is 3. Maximum degree is 3. So now, so we get that we need at most 3 colors. So now question is, so now we need at most 3 colors. So can we color, so we need at most 3 colors, we get it. Now can we color this graph using 2 colors? Can we color this graph using 2 colors?
No, ma'am.
Why? Why no?
If A and D are colored with different colors,
Yes.
then C must have another color.
Yes, you are right. So if A and D have different colors, then this is E vessel. So E should be given a other color than red, blue. Because this is an odd cycle. So we see that this graph has an odd cycle, ADE. So we need at least 3 colors. And since maximum degree is 3, so the chromatic number is less than equal to 3, and it is also greater than equal to 3. So in this manner we see that chromatic number will come out to be 3. Now can you give me also a coloring of this graph? So we have colored 3 vertices. Now what should be the, so this, if we use this result, we see that we can use 3 colors to color the vertices. So, so give me a coloring. So we have color red, blue and green, and we give red color to A, blue color to D, green to E color. What should be the colors for B, C and F? So we should be able to color this graph with three colors.
B with blue,
Yeah. B, B with blue,
F with red,
F with red,
C with green.
C with green. Yes, good. So we see that we can color this graph with, color the vertices of graph with 3 colors, and since it has an odd cycle we need at least 3 color. So we see that chromatic number is coming out to be 3. Now what are the possibilities for chromatic index? It is either 3 or 4. Now question is, can we use 3 colors to color the edges of this graph? If we can do that, then we get that the chromatic index is 3.
Yes, we can do, ma'am.
Okay, so what are your colorings then?
AB with one color, AB, CF, and DC.
AB, CF and,
Sorry, EF, EF.
okay, AB, EF and, okay, so what now, what all the, so AB and EF have same colors.
EF and CD.
Okay, you want to color the same color to CD also. Okay, now the other color. So basically, so suppose we want to color this, suppose we want to color this graph with 3 colors. So how will we do this? So first we look at the vertex. So suppose we look vertex D. Now we have 3 edges which are adjacent to 3 edges coming from D. So all these 3 edges should have different color. So we'll use 3 colors to this. So this should have a different, so okay, maybe. So this edge should have suppose color 1. So DA, DE and DC, all these 3 edges should have different color. C1, C2, C3. Now this edge AE. What about edge AE? Since C1 it ends, this edge AE cannot have C1 color, C2 color, so this should also have C3 color.
C3.
And now we see that AD and AE have C1, C3. So there is just one option for AB, which is C2. Now if we look at this one, EF edge, C2 is already covered, C3 is also covered. So there is just one option for EF also, which is C1. Now if we look at BF, so AB is colored C2, EF is colored C1. So BF also has only one option, which is C3. Now if we look at BC, so what is the possibility for BC?
C1.
C1, because C2, C3 are already colors, so C1. And similarly for FC, C3 is there, C1 is there, so it is C2. So we see that we can color, we can use 3 colors. We can use 3 colors to color the edges of this graph. So the chromatic index is coming out to be 3. C1, C3 and so is this clear? Is this question clear to everyone?
Yes.
Okay. So the next question is this. So you have to tell it if it is true or false. So the first is, in an edge coloring of G, edges of same color form a matching in G. True or false? And I have also recalled the definition of matching. So what do you think? Is it true or false?
Yes.
It's true. You're saying it's true, right? So everyone thinks it's true? First question.
False, ma'am.
Okay, why false?
From the definition of matching.
So see, matching is a so the question is that if we have an edge coloring of G and if we fix one color, say red, so all the red edges will form a matching. Is it true or false? So from the definition, it is true, right? Because matching is so if all if we have that all the so suppose if we are fixing a color red, so can two red edges have a common vertex? Can two red edges have a common vertex?
No.
So that means it forms a matching, right? Because matching is also a subset of edges such that no two edges have a common vertex. Oh, okay. So okay, the definition is no two edges in M have same vertex. So this was the so that's why the confusion. So matching we have done in earlier classes. By matching we mean that matching is the set of edges such that no two edges have same vertex. And if we have red edges, those red edges cannot like no so no those edges cannot share a common vertex. Therefore we see that therefore we see that the edges of same color will form a matching. And now the second, so hence it is true just by the definition. And second part is, if size of maximum matching in G is M, then can we say that number of edges of same color in G should be less than or equal to M? True or false? So it is also true. This follows from the first part. So first we see that if we have edges of same color, they are forming a matching. So since they are forming a matching, then the number of edges should be less than equal to the number of edges in the maximum matching. Therefore, this is also true. So is this question clear? Any confusion in this question? Okay. No.
No, clear now.
Okay. So now this is also a true false question. So first is, chromatic number equals maximum degree or maximum degree plus 1. True or false? So chromatic number is basically chi g. So we are saying that there are only two possibilities for chi g, either a maximum degree or maximum degree plus 1. So is it true or false? What do you think?
True, true.
This is chi g, chromatic number.
It is less than or equal to maybe, not exactly equals.
Yes. So the theorem says that it is less than equal to maximum degree plus 1. So, if you are saying that this is false, then can you give an example? Can you give an example of a graph in which chromatic number is strictly less than maximum degree?
You can take example of a star.
Okay. Wait. So star as in wheel. This one you are saying?
Just a single vertex mapped to many vertices.
Okay. This one. Okay. Yes. Yes. Okay. Yeah. Huh. So yeah, if we take this, so we see that maximum degree will be equal to 5. But we need only two colors. We can take the two colors. So therefore first statement is false. Good. So this is fine. So what about the second statement? Chromatic index equals maximum degree and maximum degree plus 1. Maximum degree or maximum degree plus 1. Is it true or false? So first statement,
True.
she has shown us the example which says that we can have a graph in which chromatic number is neither equal to maximum degree nor equal to maximum degree plus 1. So now what about B? B is true. Yes. So why is it true? Because this is one of the theorem we have done
There.
in the lectures, that chromatic index is greater than equal to maximum degree and less than equal to maximum degree plus 1, which only gives us two options. Either it is equal to maximum degree or maximum degree plus 1. Good. So this is that. Now the next question is this. So we are given that G is a simple graph on n vertices, and we are also given that G is deregular. We have to show that chromatic number is greater than equal to n minus d. So how can we show this? So first of all, if G is deregular, what do we mean by that? What is the meaning of deregular?
Each vertex have the degree D.
Yes, okay. So that means degree V is equal to D. Now, so we have to show this. So let's try this. Suppose chromatic number is R. Suppose chromatic number is R. So that is, we need C1 color, C2 color, CR colors. Now let's try to estimate. Let's try to see. Suppose we have n vertices. We have n vertices and chromatic number of this graph is suppose R. So suppose I am coloring V1 with one color C1. So what is, so V1 is given color to C1. Now V1 is adjacent to how many vertices? What is the degree of V1? So V1 is adjacent to how many vertices? D vertices, right? So V2, V3, say VD plus 1. And we have total n vertices. So we have VD plus 2 and Vn. So this is the, so if I am giving colors V1, if I am giving color C1 to V1, so do we have any bound on the number of vertices of color C1? Upper or lower bound? Can we say that? So that is, can we have like any bound, like how many vertices, at most how many vertices can have C1 color? So can any of these vertices have color C1, V2, V3 or Vd plus 1? So if I am
No.
giving, so if I am giving V1 color to if I am giving C1 color to V1, what all vertices are allowed to have color V1? At most, what all vertices are allowed to have color V1? Color C1, first color.
Which are not adjacent to
Which are not
V1.
adjacent to V1. Very right, very good. So we have, so basically we see that number of vertices of color Ci should be less than equal to n minus d, because if I have given one color to one vertex, then all these adjacent vertices cannot have that same color. So we have left with that other vertices should have this color. So is this clear? This much is clear, that number of vertices of one color should be less than equal to n minus d.
Yes, ma'am.
We can either have V1 or Vd plus, so this. So now how many colors do we have? So if it can be colored with R vertices, so we have that. So we have that R, so if we sum over colors, sigma Ci, if MCI is the number of vertices of color Ci, then we have that total vertices are m. So if we sum over R colors, we get this I equal to R, this is n. And now from this we have this bound, that MCI, that number of vertices of same color should be less than equal to n minus d. So now did we get our answer? Did we get what we wanted to prove? So we have that n is equal to sigma MCI, I going from 1 to R, and all these numbers are less than equal to n minus d. So this is R times n minus d. So we get that n is less than equal to R times n minus d. And what was R? R was the chromatic number. R was the chromatic number. So we see that R is greater than equal to n by n minus d. So we have shown this. So this was what we wanted to show. So is this question clear to everyone?
Yes, ma'am.
Okay. So now let's revise the planar graphs, and then we'll do some questions on planar graphs. So what is a planar graph? A planar graph is a graph G which can be drawn so that no two edges intersect. So if a graph can be drawn in a manner such that we have no overlapping edges, that is, they are not intersecting, then we see that such a graph is planar. So we see, so for example, this is C4, or if we take any cycle can be drawn in a manner, if we have any cycle, it can be drawn in a manner such that no two edges are intersecting. Therefore we see that cycles are example of planar graph. And if we look at K4, if we look at this picture, in this picture these two edges are intersecting, but this K4 have a different representation like this. So this is also a representation of K4. These two graphs are isomorph. So we have this representation possible in which no two edges are intersecting. So we see that K4 is also planar. So this is the definition of planar graph. That is, if a particular graph can be drawn in a manner such that no two edges are intersecting, then that graph is a planar graph. And we have some Euler formula for planar graph. That is, if we look at the number of vertices and if we add number of vertices and number of faces and subtract the edges, then the Euler formula says that V minus E plus F is equal to 2. So in these examples, see Cn. So since these two are planar graph, they should verify they should satisfy the Euler formula. So for Cn, we see number of vertices are n, and if it is a cycle, the number of edges are also n. But why the number of faces are 2? So can anybody tell me what are the two faces in Cn?
Inside Cn and outside Cn.
Yes,
Two faces.
two faces. So that is important. So we also have to count the face which is outside. So we see that this is the face 1 and this is face 2. So it has two faces, and now if we look at the Euler formula, let's see if it is verified. So n minus n plus 2. So we see the Euler's formula is satisfied for Cn. And similarly for K4 also we can see this. So K4 has 4 vertices, 6 edges. And how many faces do K4 have? So what are the number of faces for K4?
4.
4. These are basically these 3 triangles and the outside portion. And for this also we see that vertices minus edges plus faces. We are getting 2. Now this is so basically if we want to see some graph is planar or not, now this is first of all they should satisfy the planar graphs satisfy this Euler formula. Now we also have some relations between EV and F for planar graphs. So if we want to see some graph is planar or not, we check if these inequalities are satisfied. So if these inequalities are not satisfied, then we can directly say that that given graph is non-planar. So what are these inequalities? So first is this one, that if G is a planar graph, then the number of edges should be less than equal to 3 times number of vertices minus 6. And moreover, this inequality can be improved if G is a planar graph, G has no triangles and is a planar graph. So we are talking about planar graphs also. Additionally to planar graph, it has no triangles, then the number of edges should be less than equal to 2b minus 4. And using these two inequalities, we can show that K5 and K3 are not planar. So how can we do that? So how many edges do K5 have? So what are the number of edges in K5?
Ten.
10. And number of vertices are 5. So the LHS is 10 and RHS is 3 into 3, vertices are 5, K5. So we have 5 vertices. So what is the RHS? RHS is 3 into 5 minus 6, which is 15 minus 6, 9. So we see that 10 is not less than equal to 9. Therefore, K5 is not planar. So what about K33? How can we show that K33 is not planar? So since since for planar graph E should be less than equal to 3v minus 6, and for k5 this inequality is not satisfied, we can say that k5 is not planar. But what about k33? Why k33 is not planar? Here k33 is complete bipartite graph. So what are the number of vertices in k33? 6. And number of edges? So k33 is basically, we have two partitions. First has 3 edges and first have 3 vertices, second have 3 vertices. And
9 edges.
yes, and all the because in each it is number of edges in kmn is mn. So number of edges in k33 are 9. So if we look at the first inequality, 9 is less than equal to 3 into 6, 18, 12. So first inequality is satisfied. Therefore from this we cannot conclude that k33 is not planar. But since it is a bipartite graph, it cannot have any triangle. A bipartite graph cannot have an odd cycle. So this if it is planar, it should satisfy this inequality also. But if we see that this inequality, this RHS will come out to be 12 minus 4, 8. This is not true. Therefore from now k33, because it has no triangles, it should satisfy this inequality. But since it is not satisfying this inequality, we can say that k33 is not planar. So is it clear why k5 and k33 are not planar?
Ma'am, in that K5, you
Yes.
did that LHS and RHS.
Yes.
That RHS thing, how it became 9, got stuck there.
So this is E is less than equal to 3v minus 6, right? So 3v is 5. So 3 into 5, 15 minus 6 is 9. I was checking
Okay,
this.
got it.
Yes. So since k5, so if k5 was planar, then the number of edges should be less than equal to 3v minus 6. But since this is not satisfied, since 10 is not less 10 is not less than equal to 9, so k5 is not satisfying this property. Therefore k5 cannot be planar, because for planar graphs this should be satisfied. Is it clear?
Understood, ma'am.
Okay. But for k33 we see that first inequality is satisfied. So we cannot conclude from the first inequality whether k33 is planar or not. But for k33 we'll use the improved thing. Since k33 has no triangles, we also have this result that if it is a planar graph with no triangles, then number of edges should be less than equal to 2v minus 1. And if we look at the second thing, so this inequality is not satisfied. Hence, we see that this k33 is not planar also. And we also have some nice characterization of planar graph. So we have a necessary and sufficient condition that G is planar if and only if G does not contain a subgraph which is edge contractible to K5 or K33. So this is coming because, first of all, one thing is clear that K5, if it has a subgraph which is either which is isomorphic to K5 or K33, then it cannot be planar, because a subgraph of a planar graph is also a planar graph. But this theorem is saying much more. It is saying that if G is planar, then G should not have any subgraph which is edge contractible to K5 or K33. So this theorem is useful when we want to show some graph is non-planar. So if we want to show that some graph is non-planar, first of all, we can use one or two inequalities that are there. So that is, we calculate the number of edges and number of vertices. If a planar graph does not satisfy this inequality, if a graph does not satisfy this inequality 1, then we can say that that graph is planar. But what if it is satisfying this inequality? Then we look at our graph and we check if that graph has a if that graph has a subgraph which is contractible to k5 or k33. If such thing happens, then we can say that graph is not planar. And if we are, so now what do we mean by edge contractible? Edge contractible is like this. So if we have some edges a, b, c, and if we are contracting the edge AB, that means A and B are becoming one vertex. And what will be the edges going from AB? So if we have this kind of thing, if we have this graph and we are contracting the edge AB, that means that any vertex which is adjacent to either A or B will give us an edge. So if we contract AB, the resultant graph will be like this. So so we see that D and C are adjacent to A, so D and C will also be adjacent to AB, and DC is also an edge. So after contracting, we'll get this. So now the theorem is saying that if we are given a graph and after contracting some edges, we are getting we see that k5 is sitting in the graph or k33 is sitting inside that graph, then we can say that the graph is non-planar. So for example, if we look at this graph, and if we contract this edge CD, then the resultant graph will be like this. So now, is this graph planar? After contracting, is this graph planar? So what do you
Non-planar.
non-planar, because we see that there is a k5 sitting inside. So k5 is a subgraph of this graph. Therefore, this graph cannot be planar. So basically, if we have to show some graph is non-planar, we have to see that if after contracting some edges, we are getting a copy of k33 or k5. If we are getting that, then we can directly claim that that graph won't be planar. Okay, so now let's do some questions. So first question is this: true or false that if G is a bipartite graph and if it has edges greater than equal to 2v minus 4, then G is not planar. True or false?
True.
Okay, so you are saying true. Why is it true?
Because bipartite graph is a simple graph, and every simple graph has this property is less than equal to 2v minus 4, then we can say that G is not, if this property not satisfied, then we can say that G is not planar.
So no. So bipartite graph is a simple graph. You are right. But the bound that we did was this. The result was that if G is a planar graph,
Or
then
yes,
E
no
is
triangle.
less than equal to 3v minus 6. And the second result was that if G is a planar graph with no triangles, then number of edges should be less than equal to 2v minus 4. So now can anybody say why it is true or false? Why is it true or... So G is a bipartite graph.
Any bipartite graph cannot contain triangle.
Yes, you are right. So any bipartite graph will not contain triangles. And so if it was a planar graph, then the number of edges should be less than equal to 2v minus 4. But since we are given that number of edges are greater than 2v minus 4. So this inequality is not satisfied. Therefore, we can say that G is not planar. So this is true. So, so so what somebody was asking earlier, his approach was correct, but he just had to add that G is a planar graph. G is a simple graph with no triangles. And for such graphs to be planar, the number of edges should be less than equal to 2v minus 4. So is this question clear to everyone? Okay. Now next question is, for what values of n is Kn planar? So what about, let's try. What about K2? Is K2 planar?
Yes.
Okay. So K2 is planar. What about K3? Is K3
Yes.
planar? Yes. And K4 we already, so K4 is this. So is K4 planar?
Yes.
Because it is isomorphic to this. And we see that it has a drawing in which no two edges are intersecting. And K5 is not planar. This we have already seen. What about Kn greater than, if n is greater than equal to 5? Is it planar? That is K6, K7, K8. Can K6, K7, K8 be planar?
Non-planar.
Okay, now you'll have to give a reason also. Why do you think K6, K7, K8 are non-planar?
K6 we can contract a single edge, single vertex.
Yes.
If we contract only two vertices, then we'll get
Yes, you are right.
F5.
Or like without contracting also we can say that Kn, if it has more than if it has more than 5 vertices, if we pick any 5 vertices, subgraph induced by that 5 vertices will give us a K5. And if a graph has a K5 as its subgraph, that graph cannot be planar. So hence we see that, so if, and the other reason is also fine, that we can contract it to get n5. So Kn, if n is greater than equal to 5, contains K5 as a subgraph. And our theorem says that G is planar if and only if G does not contain any subgraph which is edge contractible to K5 or K33. So we see that Kn n greater than equal to 5 is not planar. And if it is less than 5, if it is strictly less than 5, we have shown that it is planar. So is this question also clear to everyone? Okay. So now we have seen for what values of n is Kn planar. Now let's try to classify the complete bipartite graphs also. That is, for what values of Kmn will be Kmn planar. So first is a true false question. If m and n are both greater than equal to 3, then Kmn is not planar. True or false?
True, ma'am.
True. Why?
Because graph contains the K33 as a subgraph, all graphs.
Yes, yes, you're right. So since the vertices are in both the partition, vertices are greater than equal to 3, and if we pick 3 vertices from one partition and 3 from other, the subgraph induced by that will be K33. So since Kmn contains K33, contains K33 as a subgraph, such Kmn are not planar. So we see that if both of them are greater than equal to 3, then they are not planar. But what if one of them is less than equal to 3? Then what can we say? So the first question is, so the B part is that, so we have seen that if both the numbers are greater than equal to 3, it is not planar. So the remaining cases are when one of them is less than equal to 3. So first case is k and 2. So suppose we have k, so k and 2 looks like this. So we have n vertices here, 2 vertices here, and this is the graph. So what do you think? Is k and 2 planar? Is k and 2 planar? So if you think it is a planar graph, then you should be able to draw it in a manner such that no two edges are intersecting. So
Yeah, it's planar.
okay, it's planar. So you'll have to give a planar drawing also. What will be the drawing? So if you think it is, why do you think it is planar first of all?
We can draw it in plane.
So how can we draw it? Like,
Like we take first as E, where vertex E.
okay, we take vertex E.
All other vertices are in below E.
Okay, all the other vertex are below E. So A, B, C, D. And where should I put F?
First of all, we have to join these and then we decide.
Okay. Now what about F?
Now F is put in parallel to E.
Here, right. Parallel to E here, or where do you want to put F?
Opposite side to E.
Right,
Yes,
you are right.
yes. So now if we do this, so we see, that k and 2 is planar, and this we can do with any number of vertices. So this is k for 2. So basically so the one partition we put here and other we here. So we see that k and 2 is planar. So the second thing is true. And what about k? So the C part is saying that k and 1 is not planar. True or false? So the remaining, so for if n, so is k and 1 planar?
Yes.
So this is clearly false because k and 1 looks like this. And this is a planar graph because there no two edges are intersecting. So from this we can conclude that KMN is planar if and only if. So basically KMN is planar if and only if one of these numbers should be strictly less than 3. Then it is planar. But if both the numbers are greater than equal to 3, then the complete bipartite graph is non-planar. So is this question clear to everyone?
Yes.
Okay. So now the next
Then
one.
K N1 will have only one face. No?
Sorry.
K N1 will have only one face.
Yes, we'll see. K and 1 will have only one face. Yes, you are right. So now the next question is verify Euler's formula for Kn2 and Kn1. So let's first do it for Kn1 since somebody asked only. So Kn1 is this. So we have n vertices in first bipartition and one vertex in the other partition. So what are the number of vertices in Kn1?
N plus 1.
N
N plus.
Number of edges? Number of edges?
N.
N. And faces? Number of faces?
One.
1. Because there is no interior. There is just one exterior face. So now is the Euler formula satisfied? Vertices minus edges plus faces. So we are getting 2. So we see that for Kn1 Euler formula is satisfied. What about Kn2? So Kn2, as we have seen, it looks like this. So these are n vertices and the other partition has this. So what are the number of vertices for Kn2?
n plus 2.
Now number of vertices are n plus 2. Number of edges?
2n.
What about faces? Number of faces?
n plus 1.
Why n plus 1? So suppose if I am taking K32. So this is this, right? So if there are 3 vertices, so if there are 3, so how many interior portion we are getting?
It's 2 interior portion. 3.
3. So we see, so basically if you have n points, so there is no line between them though. So we see that if you have n points and there are these divisions, so in the interior how many faces are there? If there are, so for 3 we see that there are 2 faces in the interior, but if there are n vertices in the middle, how many interior faces are there?
n minus 1.
N minus 1, and then there is one exterior face also. So the total number of faces are n. And if we look at the now Euler's formula, it will be vertices minus edges plus faces. So is the Euler formula satisfied? Yes. So we have n plus n 2n. So this is 2. So we see that it is satisfied. Okay, first of all we'll do this. So now this is the next question. So we are given that this is a planar graph, but now we have to draw a planar drawing of this. So how can we draw a planar drawing of this graph?
Using biportrait graph.
Using?
Concept of biportrait graph maybe.
Okay. How? Okay. But is this graph bipartite? This graph has a triangle, so it need not be bipartite. So one way is, so we have this cycle. So now we see that all the intersections which are happening are inside this cycle. So the way to do it is, we'll have to bring some of the edges in the inside to the outside, the edges which are intersecting to the inside. So let's try to do this. So now we'll start with any edge. Suppose I'm starting, so basically all the intersections which are happening are inside, so we'll have to bring some edges outside. So suppose I'm starting with this edge 1 3. So now let's, instead of 1 3 in inside, let's make it outside. Okay, so now we see this, but this 1 3 edge was already intersecting with these 3 edges. So if we bring these edges outside, they'll intersect outside also. So we'll keep these edges in the inside only. So now the question is, what all edges can we bring outside so that this graph becomes planar? This graph is planar so that we have a plane drawing of this graph. So I have brought one edge outside, 1 3. But I am saying like now this 1 3 edge was intersecting with 2 8, 2 7 and 2 5. So we should not bring any of those outside, because if we'll bring any of those outside, they will intersect. So we have to keep these 3 edges in the inside. Now, but these 3 edges are intersecting with 1 4 and 1 5. So let's bring them, let's bring 1, 4 and 1, 5 outside then. So now I have to bring 1, 4 and 1, 5 outside in a manner such that they don't intersect. So if I take this like this, 1, 4 and 1, 5. Now do we have any more self intersections? Yes. So we have this other edge 5, 8 and 6, 8. So any ideas how can we do this now? How can we make it planar? How can we have a plane drawing? Like what we have done some things similar to this. So we have these two edges are also intersecting. So we have to do something with the
Just between 8, 6.
sorry.
8, 8, 6 can be brought out.
Yes. Yes.
Excellent.
8. Yes, we can bring 8, 6 out. Okay.
8, 6, 8, 5.
So if we bring 8, 6 out, and we can also bring 8, 5 out. So we see that we have a plane. Now are any is there any self intersection?
No.
So we see that this is plane. So if we have some some Hamiltonian graph like this, basically that all the vertices have cycle. So we can, to check if it is planar or not, we can do this. So we can try bringing some edges outside, and if there are like, so 1, 3 I brought outside, like we can, like if I brought 1, 3 outside, but this was in, so but we don't have to bring those edges outside which is intersecting with, because if I brought 1, 3 and it was intersecting with 2, 8, so if I brought 2, 8 outside, there is no way in which it can be brought outside and it is not intersecting. So we see that in this manner we have constructed a plane drawing of this graph. So this is a planar graph. So now the next question is this: is G planar? So what do you think? So first of all, let's try to see the inequality. So how many edges does this graph have? So if it was planar, then it should satisfy those inequalities. If it is not satisfying the inequality 1, then we can say that it is not planar. So is it satisfying this inequality that E is less than equal to 3V minus 6? So is it satisfying this inequality?
Satisfying.
Okay, so what were your number of edges?
10.
10. I think there are 11. 1, 2, 3. There are 11 edges.
11 inches.
And number of vertices are 8. E is equal to 11. Number of vertices are 8. So we see that 11 is less than equal to 24 minus 6, which is 18. So first inequality is satisfied. So from that we cannot, so no conclusion. Can we apply second inequality also to this graph? Does this graph have triangles? Since this graph has no triangles, so we can use the second inequality also. But we see that number of edges are 11. 2 into 2v minus 4. 16 minus 4. But second inequality is also satisfied. So we cannot conclude from here also. So now we have to check. Now we have to either make a plane drawing of it, or we have to show that it is edge contractible to K33 or K5 to say that it is planar or non-planar. So what do you think? Is it planar or not? There's one more thing. There's one more thing. So in this inequality, like if we cannot directly say, so the uh, so in this inequality you see, since this graph has no triangles, number of edges should be less than equal to this. So we have 11 edges. Oh, sorry, we'll have 11 edges, but this inequality is 12. So what if we contract one edge? So I'm saying, so since it has, see, so this if we look at this graph has 11 edges. So if we'll contract an edge, then number of vertices will decrease by 1, and number of edges will also decrease by 1. But that won't help us. So
Number of edges may be decreased more or less.
more also, yes. So okay. So now we see, like if we want to do, so these are the two things. So if we want to, if we want to bring the 7 4 outside, we cannot do that without intersecting. And similarly for 3 8. So this graph seems non-planar. Now we just have to show that it is non-planar. So basically, after contracting some edges, we have to either say that it is it has a subgraph, K33 or K44. Okay, so since this graph, we see that it has no triangles, so let's try to contract some edges. So first of all, let's try to see if it is a bipartite graph. So now this graph has 11 edges. Now this graph has 11 edges. So if it was edge contractible to K5, then after contracting one edge, we should get K5.
Ma'am, can we interchange 7 and 8, the places of the vertices? Is it possible?
7 and 8 as in how to interchange? No.
Interchange.
Oh, no. So I'm okay. You wanted to make it like this, right?
Uh,
But we have to keep the no. Like if we have to change it in a manner that so that no other properties are also isolated. So if you have to, basically you are saying that there should we but this interchanging is not allowed. No, we cannot do that. Like,
oh,
so if you are in, like, you'll have to make a graph isomorphism. So this does not look like that. If it is non-planar, it will go to K5. Let's try to see for K33. So let's see. So since it has this graph has almost all the cycles even. So let's try to first see if it is a bipartite graph and try to make it and then see if we can contract some edges to get K33. Okay. So if I'm putting one here. So first of all, if this is a bipartite graph because it has no odd cycles. So we can see that this graph has no odd cycles. It is a bipartite graph. So now first we'll take the bipartitions. So if I'm putting 1 in here, 2 will go to the second bipartition. So this is a bipartite graph. So can you give me the bipartitions? This graph we see has no odd cycle, so it is a bipartite graph. So what should be the two bipartitions? Like in set A, what all vertices should be there? So do you understand the question? So first we are trying to draw it like a bipartite graph. Yeah. Yes. So
1, 6, 7.
So you are
One
saying
side.
1, 6. Okay, 1, 6, 7. So yeah. So now if 1 is there, then the 2 should go to the other side.
3, 3.
1, 6, 7 and 3. Okay. So this will give 2, 4, 5, 8. Now 1 is adjacent to 2. 1 is adjacent to 2. 1 is adjacent to 2 and 1 is also adjacent to 5. Now if we do this, for now 6 is adjacent to 2, 4 and 8. 6 is adjacent to 2, 4 and 8. So this has degree 2, this has degree 3. 7 is adjacent to 8, 5. Adjacent to 8, 5, 4. And 3 is adjacent to 4, 5 and 8. 4, 8. So this is the graph. So we see that this has 3 degree, this has 3 degree and 2 has 2 degree. So 3, 6, 9. So this is the graph. Now do you think it is, now can we contract some edges to get K33? Copy, like contracting some edges, deleting some word, like after can we contract some edges to get K33 as a subgraph? Any now it is clear, I guess, from the so we have drawn an
Yes,
isomorphic
it's
copy.
possible.
So
Yes.
what edges do you think we should contract?
1, 2, 2, 6.
Okay, so you are saying we contract 1, 2, 6. 1, 2 and 2, 6. Okay. So if we, first of all, if we contract 1, 2. So controls. So now if we contract 1 and 2, the edge 1, 2. So now that means 1 and 2 is becoming same vertex. So now 1 was adjacent to 2 and 1 was adjacent to 5. 2 is also adjacent to 6. So we will have this edge also. Now what we are doing, we are in the second step, we are also contracting this edge. So if we contract this edge, if we contract this edge, then this will be the new graph. 1, 2, 6. So now we are getting K33. So after contracting 1, 2 and 2, 6, we get K33. Therefore we see that this graph is
As
non-planar.
5.
It is not planar. This is not planar.
One edge is missing, ma'am. 1 to 6 to 5 edge there.
Huh? Sorry? Okay, yeah. Okay, there's one edge missing. Yeah. So there is one edge missing. So we get K33 as a subgraph. So yes, so you are right. So if we 1, 2, 6 are becoming a common vertex and 1 and 5 were adjacent. So this will also be an edge. And we are getting K33 as a subgraph. So if we delete this edge, then we are getting K33. Or if we just look at this graph G minus, if we look at the graph G minus this edge E, G prime minus E, then we are getting K33. Therefore, this graph is not planar. So is this question clear why this is not planar? Is it clear to everyone?
Yes, ma'am.
Okay. Okay, so now there was one more question left. Yes. Now we have to show this. First question is this, that if G is a planar graph with no triangles, then show that G has a vertex of degree at most 3. So this is the first part. So how can we prove this? So first of all, if G is a planar graph with no triangles, then what is the relation between V and E? If G is a planar graph with no triangles, what is the relation between V and E?
E is less than or equal to 2V.
Then E is less than equal to 2V minus 4. So this is first thing. Now we have to show that G has a vertex of degree at most 3. That means to show there exists a vertex V such that degree of V is less than equal to 3. So how will we show this? Hint, I am also giving you a hint, and then you can, we have to show it by contradiction. Show it by contradiction. So first of all, if we want to show that there is a vertex of degree less than equal to 3. So suppose this is not true. Suppose there is no vertex of degree less than equal to 3. Then what does that mean? What is the degree of each vertex?
Greater than 3.
Greater than 3 or greater than equal to 4.
Equal to 4.
Okay. So now, so suppose dv, suppose result is not true, then degree of each vertex is greater than equal to 4. Now what is the sum of degrees? Then sum of degrees will be greater than equal to 4v. And what is the sum of degrees?
Twice number of it.
Twice number of. So we get that 2e is greater than equal to 4v. 2e is greater than equal to 4v, and from this we get that e is greater than equal to 2v. So is it possible that if G is a planar graph with no triangle, can number of edges be greater than equal to 2v? No, because but since it is planar, e is less than equal to 2v minus 4. Therefore, it cannot be greater than equal to 2v minus 4. So we get a contradiction. Therefore, every planar graph with no triangles has a vertex of degree less than equal to 3. So is this clear? The first part of the question. Now using this, can we show that planar graphs which have no triangles are not four-colorable? Can we show this? So this is, so maybe, so this was done in class. So do you know what is a k-degenerate graph? Does anybody know what is the definition of k-degenerate graph? It was mentioned in one of the lectures. Yeah. So what is the definition of k-degenerate graph? Okay, so I'll tell you. So we have to show first that planar graph with no triangles are four-colorable. Now k-degenerate graph is basically that G is k-degenerate if every subgraph of G has a vertex of degree less than equal to k. And then we also have a result in our lectures that if G is k-degenerate, then G is k plus 1 colorable. Now using these two definitions at the first part of the theorem, that is first part of the result that we have exercise that we have shown, that if it is a planar graph with no triangle, then there exists a vertex of degree less than equal to 3. So we have already shown this. So now do you think that, so k-degenerate graph is this, that not only G but all the subgraphs of G also satisfy this property, that G has a vertex of degree less than equal to k. So can you say that if G is a planar graph with no triangle, then it is a 3-degenerate graph? So we have shown for that, for G, that if G is a planar graph with no triangle, then there exists a vertex of degree less than equal to 3. But is it true for its subgraphs also? So first of all, is a subgraph of a planar graph planar? Is subgraph of planar graph planar?
Yes, subgraph of a planar graph is planar.
Okay. And if a original graph has no triangles, then will the subgraph
Will also not have triangles.
so we see that subgraph of planar graph with no triangles are also planar graph with no triangles. So now can we say that planar graph with no triangles are 3-degenerate then? So this shows that planar graphs with no triangles are 3 degenerate. And now this is the result in class, that if G is K degenerate, then G is K plus 1 colorable. So we get that planar graph with no triangle is 4 colorable. So now is it clear? Is this part clear to everyone?
Yes, ma'am.
Okay, so this was all for today. This was all for today. Yes. Any questions? Any questions in any of the problems that we discussed today?
Okay, ma'am. Thank you.
Okay, so if there are no questions, then I'll end.
Problem